Today we'll learn about ionic bonding and the ionic compounds that will result from that, covalent bonding and the molecules that will result from that, and then the Lewis dot structures of those molecules. So, lithium fluoride, what does that look like, and where are electrons around lithium and fluoride during that? So we have a metal reacting with a nonmetal, and they have very large differences in electronegativity. Nonmetals are more electronegative than metals, and so they pull electron density towards them significantly more than the other. So when you have a metal and nonmetal together, that significant difference in electronegativity will result in a transfer of electrons from the metal to the nonmetal. When that happens, if you move that electron over to fluorine, you'll be changing the electron configurations of these species and hence their stability. You know, lithium might start out with an electron configuration of 1s2, 2s1. That is not a noble gas configuration. You know, it's not the same as helium, which is 1s2. And fluorine is also not yet stable, 1s2, 2s2, 2p5. Neither of these are stable, but if lithium sends an electron over to fluorine, lithium will now be missing that electron and have now the same electron configuration as helium, 1s2. And fluoride will now have the same electron configuration as neon, 1s2, 2s2, 2p6. They will now become more stable, and they will be able to stick together because of their charge. Having lost a negative electron, there's now going to be more positive protons on lithium than negative electrons, and hence there's a +1 charge. There's 3 protons and 2 electrons left on it, so 3 minus 2 +1 charge. And fluorine, having gained 1 negative electron, will now have a -1 charge. We will have an ionic compound here. It's a compound composed of these ions, and there is ionic bonding between them, the attraction between the positive and negative ions. Positive and negative attract each other. So when you have a metal and nonmetal, this is a memorized thing, you'll get ionic compounds because of a full transfer of electrons. But if you're dealing with a compound or an element actually also, where you have 2 nonmetals together, then you're going to likely have a molecular compound. So a molecular compound does not have ions. Instead, electrons are shared between the atoms, and therefore there's a covalent bonds holding them together instead of ionic bonds. So nitrogen, its electron configuration is 1s2, 2s2, 2p1. It has 5 valence electrons. Actually, correction, it's 2p3. It has 5 valence electrons, 2 in the 2s subshell and 3 in the 2p subshell. So those 5 valence electrons are represented by these 5 Lewis dots. Each of these dots is a valence electron. Nitrogen has 5 valence dots, and this nitrogen has 5 valence dots. Neither of these is stable yet. Atoms will tend to gain or lose or share electrons until they get a noble gas configuration. Until, for most of them, they get 8 valence electrons. Each of these only right now has 5. And so instead of giving and taking electrons, which would not make both of these atoms stable, instead the electrons will be shared. Now this nitrogen over here has 5 valence electrons, but it needs 8 to have a full valence shell and be stable. So it can have a transfer of an electron, another electron, and another electron in towards it. Then this nitrogen, instead of having 5, will have 3 more near it. It will have a total of 8 valence electrons. And then similarly, this nitrogen has 5 valence electrons, but if you send 1, 2, 3 electrons in towards it, it will also now have 8 valence electrons around it. The electrons that were sent in will be now in between those nitrogen atoms. They will be in a covalent bond, a sharing of electrons. Co means sharing, and then valent, sharing of valence electrons. So you can now see that nitrogen on the left has 8 valence electrons around it, and this nitrogen on the right also has 8 valence electrons around it. These are all now going to be much more stable. It's nice to have 8 valence electrons, the same as the most nearby noble gas, neon. Here, principal energy level 2 is totally full, 2s2, 2p6, stabilizing. So you'll find that there are covalent bonds in molecules. Covalent bonds can be in 1 line, 2 line, or 3 lines. Overall, the final way to draw this is to have 3 lines. Each 2 electrons that are shared are going to be 1 line. So having 6 electrons, you're going to have 3 lines in between these. That's a triple bond holding those 2 atoms together. All right. Now, ultimately, the way I just drew the Lewis dot structure, moving electrons around in that way, is oftentimes not the fastest way to do it. So here's another and likely more efficient way to draw a Lewis dot structure. Consider how many total electrons you'll need to have, total valence electrons, and make sure you have that. Nitrogen, each of those, you recall from up above, each of them started with 1, 2, 3, 4, 5 valence electrons. There were 2 of them, so there were a total of 10 of those Lewis dots to play with. So you can also kind of calculate that by saying, yes, there's 2 atoms of nitrogen. Each one has 5 valence electrons. So 2 times 5, there's a total of 10 valence electrons to play with. That's the number that are available. And then move those electrons around until you have a full valence shell in most cases. So for most elements, move them around until you have 8 valence electrons, a full octet 8. But there are exceptions. Hydrogen only needs 2 valence electrons around it. Beryllium oftentimes is most stable with 4, boron with 6. And then with elements in period 3 or greater, so like sulfur, phosphorus, chlorine, and below, those can have 8, 10, 12, 14, 16. So we want to use those 10 electrons to make sure that each of these atoms has 8 valence electrons around it. So at minimum, you're going to need to have at least 1 line, 2 electrons, holding those nitrogen atoms together. And then you could just drop some electrons in. You want to have a total of 10. So you've got 2, 4, 6, 8, 10. All right, so you've placed 10 electrons, but is this the optimal placement? Have you gotten 8 valence electrons around each of these atoms? Well, right now, the way you've placed it, this left nitrogen only has 2, 4, 6 valence electrons around it, and this right nitrogen only has 2, 4, 6 valence electrons around it. So we want to keep these 10 total electrons, but move them so that each of these atoms has 8 valence electrons around it. You can do this by maybe moving these 2 in to form a bond, and maybe moving these 2 in to form a bond. And so if you do that, then you'll have just as many electrons as before, 2, 4, 6, 8, 10, the proper number. And now you'll see that on the left you have 2, 4, 6, 8 nitrogens, and on the right you have 2, 4, 6, 8 nitrogen electrons around that nitrogen. So that is a stable Lewis dot structure. You've made sure that you have the proper total number of valence electrons, 10, and each atom has 8 valence electrons around it. So kind of moving on to new things that you may not have seen 2 years ago. Another thing to consider is the overall total formal charge, but also the formal charge on each atom. So let's bring that into the drawing of the Lewis dot structure of sulfate, SO4 2-. All right, so you want one S and you want 4 O's. You likely want to place the kind of the weird element in the center, the one that sticks out. There's only one sulfur and 4 oxygen atoms, so sulfur goes in the middle. And then also, if sometimes you have to choose, you want to put the least electronegative element in the center. Of course, hydrogen can never go in the center because it can only have one bond on it, because it only can have 2 total valence electrons around it. So we want to have this skeletal structure, and we get to play with a total of, let's see, 1 sulfur. It brings 6 valence electrons for a total of 6 from it. There's 4 oxygens. Each one brings 6 valence electrons, so we have a total of 24 electrons coming from oxygens. But also, because it's SO4 2-, there's going to be an additional 2 electrons. If it's 2-, there's 2 extra negatively charged electrons contributing to that -2 charge. So a total of 6 plus 24 plus 2, 32 electrons we get to play with. Let's see if we can place those 32 electrons and get everyone a full valence shell. So spread them out. Work in pairs. You're very rarely going to see electrons alone. They're almost always going to be in pairs, unless you're dealing with nitrogen, which can sometimes have 7 total valence electrons around it. So we have placed 2, 4, 6, 8, and then 8, and then 8, and then 8 valence electrons around sulfur. 8 times 4. There's a total of 32 electrons around this sulfate. This is the proper total number. And have we gotten everyone happy? Does everyone have a full valence shell? Well, each of these oxygen atoms has 2, 4, 6, 8 valence electrons. Ditto, ditto, ditto. And this sulfur has 2, 4, 6, 8 valence electrons. All right, so we've got a total of 32 electrons, and everyone has a total of 8 valence electrons around them. Very good. But now bringing in the new thing, minimizing formal charge and optimizing it as well. All right, so formal charge shows the fact that sometimes there's more negative electrons around an atom than there are positive protons in it. And so we can show that by showing negative charge on that thing. Or occasionally, there will be more positive than negative charge around it, and so we'll show a positive charge. What we want to deal with is the fact that sometimes one part of a molecule might have a negative charge and one part might have a positive charge, but that does not kind of optimize the charge. Ultimately, negative electrons will spread around that molecule until they're roughly avoiding each other the most and being near positive charge the most. It's best to have the least visible formal charge on a molecule. And if there have to be negative charges, you put them on the more electronegative elements. So to deal with all that, what we can first do is show the formal charges on each of our atoms, and then move them after that until we have the least formal charge. So what is formal charge? It is the atomic number of the element minus the number of total electrons belonging to that atom. So you can kind of simplify this and say, that there need to be a total, typical number of valence electrons coming from that atom that kind of accounts for any inner electrons. And then you want to subtract the total number of valence electrons that are now belonging to that atom. What do I mean here by belonging? I mean electrons that are kind of its and not the other atoms. So electrons in lone pairs on it and half the electrons in the bonds. All right, so let's run through a couple examples. What is the formal charge on this oxygen? Okay, so formal charge on oxygen? Normally you should have a total of 6 valence electrons belonging to a oxygen atom. Because it's in group 6A, it starts with 6 valence electrons typically. But right now, we've got 2, 4, 6 electrons that are definitely just its, but there's also 2 electrons that are being shared between this sulfur and this oxygen atom. And we kind of split those electrons up. One of these electrons might be belonging to the sulfur, and one of these electrons might be belonging to this oxygen. So right now we have a total of 2, 4, 6, 7 electrons belonging to this oxygen. Overall, there are more negative electrons around this oxygen than it might normally have, and hence there's more negative electrons than positive protons. There's a -1 formal charge on this oxygen. Ditto for this oxygen, and this one, and this one. But additionally, this sulfur also has a formal charge. Normally, sulfur is in group 6A, so it normally should start with 6 valence electrons. But right now, it only has belonging to it just this 1, 2, 3, 4. So there are fewer electrons around the sulfur than there would be if it were just a pure atom. And so there's a +2 overall charge on this sulfur. So this is not optimal. We want to kind of move electrons around this so that there's fewer charges shown. Electrons here are going to kind of be repelled by that negative charge. Ditto, ditto, ditto. And then they'll be attracted to that positive charge. So they're going to be spending less time around that oxygen and more time towards that sulfur. And so we can optimize this by kind of moving maybe these 2 electrons into forming a bond. So let's see what happens to formal charge after we've done that. So all these other ones are still the same. But over here we now have a double bond on the oxygen and only 2 lone pairs instead of 3. All right, so this still has a negative charge, negative formal charge. But what about this oxygen? It should normally start with 6 valence electrons, but right now it has belonging to it 2, 4, 5, 6 valence electrons. There is no formal charge on that oxygen now. That's good. You've improved this somewhat. And then on this sulfur, normally it should start with 6 valence electrons. And how many belong to it right now? 1, 2, 3, 4, 5. So there's a +1 formal charge on this sulfur. So we've made some improvement. Previously there was a +2 and there was that other negative formal charge, and now it's just a +1 and no formal charge. So we can just repeat this once more. Move electrons away from a negative formal charge and into forming a bond. Maybe we can do that with maybe these 2 electrons now. Move them in to form a bond here. So that we get the following Lewis dot structure. All right, so these oxygen atoms still have negative formal charge. This oxygen and this oxygen now have no formal charge, and this sulfur, it normally should have 6 valence electrons around it because it's in group 6A. And right now there are 1, 2, 3, 4, 5, 6 valence electrons around it. So there's just as much negative charge as there should be normally. There's no formal charge on that. So we've minimized formal charge here. We have the fewest formal charges that is possible for this overall charge of this ion. And, sulfate has a -2 overall charge, so ultimately there needs to be a 2- formal charge on that sulfate. Ultimately, the formal charges that you show should always equal the overall charge of that molecule or ion. So this is also good because we have the negative formal charges on oxygen, which is more stable place for the negative charge to be than sulfur. Oxygen is more electronegative than sulfur, so electrons will tend to hang out more towards oxygen than sulfur. All right, so this is like your final answer for the Lewis dot structure of sulfate. But did minimizing formal charge break this octet rule? We like to have 8 valence electrons. Oxygen here has 2, 4, 6, 8. Ditto, ditto, ditto. But the sulfur now has 2, 4, 6, 8, 10, 12 valence electrons around it. Is that okay? Yes, it is. Sulfur is in period 3 or greater. So it can have more than 8. Ultimately, the main thing is that you minimize formal charge.